Hello everyone. In today's video, we are going to be taking a look at the mechanism for a hydrohalogenation reaction. Okay, so a couple of notes for this reaction before we get into an example mechanism. So the first note that we need to make sure we remember about this reaction is that this reaction occurs Markovnikov style. So this is a Markovnikov reaction. And what does that mean? That means that when we are adding a hydrogen, the hydrogen is going to prefer to add to the carbon where there is more hydrogens. So when doing the hydrohalogenation reaction with an alkene, you're going to want to add the hydrogen to the side of the alkene that has more hydrogens. If both sides of the alkene are the same, then we will add the bromine to the more highly substituted side of the alkene. And we'll see an example of that later. So let's just say H adds where there are more H's. Okay. And then again, if we were using HBr as our reagent, the Br, or the other half of the hydrohalogenation, so the halogen part would add where there is more substitution on the alkene. So let's look at our first example of this mechanism. So let's take just a very basic alkene, and let's say we're going to react it with HBr. Now when you're doing these hydrohalogenations, sometimes you have to draw out the molecules in a different way, and we'll do that in just a second. So this HBr could be anything. So we could use the general form HX, where X can equal either usually chlorine, bromine, or iodine. So again, we're adding a halogen, and typically fluorine won't react in this type of mechanism, but it's still a halogen. It still technically could react in this reaction. So taking a look at our reagent, we have HBr, but in order to successfully draw the mechanism, let's draw HBr out with the bond shown, and then we will draw the lone pairs on the bromine. Now this is good practice when drawing mechanisms because you want to see where the electrons are going and where they're coming from. So the first step of this reaction is to use the double bond. The double bond, again, is an area of high electron density, and that is going to go and attack our hydrogen, like so. And then the bond between hydrogen and bromine is going to break and move to the bromine. So what does that give us? That gives us let's say we add hydrogen on this side. Now in this example, it does not matter which end of the alkene we're adding our hydrogen, because both sides of the alkene are equivalent. We have one implied hydrogen on each side as well as the methyl group on each side. So the hydrogen in this reaction could react on either side. And when we split the double bond and attack that hydrogen, the hydrogen forms on one end of where the double bond was, and on the other end of where the double bond was, we're going to get a positive charge. So we've formed a carbocation. Okay, now looking at the next step, now we have that carbocation, which is a species that does not like to exist for very long because carbon wants to have 4 bonds. So from the beginning step, remember that we broke the HBr bond and moved electrons over to the bromine. Now we have this negatively charged bromine with 4 lone pairs that is able to come and attack that positive charge. And so when we do that, we're going to get our newly bonded hydrogen and a newly bonded bromine. And then this would be the final answer, and that is how we got to the answer via the arrow pushing mechanisms. Now, if we were to see this problem and it did not ask for the mechanism, but it just asked for us to predict the product, then what we do is we take 1 hydrogen and we take the 1 bromine and we add them on opposite ends of the double bond. And this is also anti-addition. This is anti-addition, which means that the hydrogen and the bromine are going to add on opposite sides of the molecule. So let's just redraw our product. And because it's anti-addition, we see that the bromine is adding on the top and the hydrogen is adding on the bottom. That's what is meant by anti-addition. You're adding 1 on the top and 1 on the bottom, or if we had wedges and dashes, 1 would be on a wedge and 1 would be on a dash. Okay, now let's take a look at an example where our substituents on each side of the alkene are not the same. So let's say we have, now instead of 1 methyl group on both sides of the alkene, we have 2 methyl groups. And now let's do this reaction with HCl this time. So remember, for hydrohalogenations, our X can be any of the halogens. So let's do it with HCl. All right, and again, whenever we have our reagent, it's best to go ahead and draw it out in the bonded form. That way we can see what is going on. So just like before, and just like in all of these reactions, the first step is the alkene is going to attack the hydrogen. And then that bond breaks and pushes the electrons that were once in the HCl bond over to the chlorine. Okay, and now that's going to give us a carbocation. Now the question here is, where does the carbocation form? So we have 2 different options, right? We have adding the H here and putting the carbocation there, or we can get the carbocation forming on the other end of where the double bond was. So adding an H here and getting a carbocation there. So which one of these is correct? Well, if we take a step back and think about carbocation stability, here we have a secondary carbocation. Secondary because that carbon is bonded to 2 other carbons, here and here. And then when determining the order of the carbocation, we're not going to worry about the implied hydrogen that's there. There is an implied hydrogen, but we will not worry about that. In fact, let's just go ahead and get rid of that so we don't get confused. And then looking at our other carbocation, here we have a tertiary carbocation and secondary. Okay, so looking at these carbocation formations, we can see that one has more carbons bonded to it. That is going to be the more stable carbocation, so that is where the plus charge is going to exist in the molecule. So we can say that this one equals more stable. So this is going to lead to our major product. Now the secondary carbocation will form to some degree. However, that's not going to be our major product. That will be our minor product. Okay, from here, let's say we have our chlorine that we formed in the first step, and that chlorine is going to come and attack the positive charge on the tertiary carbocation, and then we are going to get our major product. Our major product being this compound. But if we were to use the other compound, if we were to use the secondary carbocation, and so let's say we had chlorine and it was attacking this carbocation, that would lead to the minor product. So our minor product would be formed by attacking that carbocation, and that would give us this compound. So both answers are correct. However, when asked to solve this mechanism, you need to indicate that one product, this one, is the major product, and the other one is the minor product. But oftentimes you will just be asked to draw the major product, so you need to put the chlorine or the halogen, whichever halogen it is, on the most substituted carbocation, and the hydrogen on the least substituted. Okay, now let's take a look at one more example, and we will make this one similar to the last one with one change. Let's draw our starting compound. This time let's do a terminal alkene. This group coming off of the alkene. Let's have a isopropyl group on the end of the alkene. And so let's do this reaction with HI. Let's get all the halogens in there. So just like before, we want to draw out the reagent, and we'll draw in our lone pairs. So just like before, our alkene is going to be attacking the hydrogen, and the HI bond is going to break and give the electrons to the iodine. Okay, from here, we're going to get a carbocation forming. And if we remember back to the last example, our carbocation is going to form on the more substituted carbon. Well, looking at the implied hydrogens present, we see that this one, this carbon on the left of the alkene, is more substituted. So that's where the carbocation will form for the major product. And in this case, as you'll see in just a second, this has to occur. So we'll get the positive charge there, and we'll say we added the hydrogen on the other carbon. Now, from here, you might think that we just add the iodine to that positive charge. However, we have to be aware of the rest of the molecule. And if we look one carbon over to this carbon, if we were to have a carbon on that carbon, that would be a tertiary carbocation, where currently we have a secondary. And coming off of this tertiary, there is an implied hydrogen. So what occurs here is a hydride shift. So we have a secondary carbocation, and we have the potential to form a tertiary if we transfer one proton or one hydrogen, so we get a hydride shift to where that hydrogen on the tertiary carbon is going to move to the carbocation, or the positive charge where there's a secondary carbocation. And so now we get a more stable carbocation being a tertiary form. And so let's just label this hydrogen to make sure we remember where it came from. I'll just give it a circle. So this hydrogen is not the one from the reagent, it's just the one from the hydride shift to form the more stable carbocation. And now we can finish the reaction with our iodine, or iodide in the ion form, where a lone pair from the iodide is going to come and attack that positive charge, and then we will get this hydrogen that added and an iodine. And if we remember where the alkene was to begin with, let's say this was our alkene, this is where the alkene was initially, but because of that hydride shift, we're not adding the iodine onto the end of that alkene. We're adding a hydrogen from the hydride shift, and then we add the iodine one carbon over on the more stable carbocation. So when you're solving these hydrohalogenation mechanisms, it's really important to be aware of your molecule and what it looks like, and see if right next to where you might have a secondary carbocation, is there the possibility to form a tertiary, or next to a primary, is there the possibility to form a secondary? Now that would be a weird example because it's not likely to happen in that case, but secondary to tertiary is very likely. So make sure you are aware of the possibility of a hydride shift to form that more stable compound to react with your free hydrogen. Okay, so in the next mechanism video that will be posted, we will be taking a look at halogenations instead of hydrohalogenations. Hydrohalogenations, we're adding a hydrogen and a halogen. In only a halogenation, we are going to be adding two halogens, so stay tuned for a mechanism video on that type of reaction.